Hi, I'm Dan, Mr. Bo, and this is our third lesson in our June Math online program. We're learning about sets and Python, and this third lesson we're going to be learning about set builder notation, complements, and intersections. So our objectives are going to be able to, one, we'll be able to write sets in set builder notation, and two, we're going to identify the complement of a set, and three, we're going to identify the intersection of a set. So you've heard about intersections a little bit before, and so that should be pretty straightforward for us, but I don't think you've heard of set builder notation before. Let's start with that. So what is set builder notation? Um, so from the website that I've linked in your Google Classroom, you can see there's a problem there, and the math teacher asked 3 students to list all of the integers greater than -3. So create sets of integers greater than -3. And they all 3 gave different answers. And I'm going to give you a second to look over them. All right, so after you've looked over them, I want you to tell me which person you think is right or wrong, and write it in the note there. It's not graded. Just do your best. Okay, so they each wrote this set using a different notation, but it turns out that they're all right, and they're all correct. And Keisha didn't write positive in front of the integers over here, but Angie did. They wrote different out to different numbers, and they both wrote an ellipsis. That's great. But Eduardo just decided to use a description. But there's a different way that can disappear, and it's called set builder, and it looks like this blue thing at the bottom, and it's has a variable, and you'll see later sometimes we say it's an element of a larger set, and then 2 dots, a colon, or possibly a bar or a pipe, and then a description of what it is. Okay, so and mathematicians love this because it's very precise. Almost all sets in math are written, defined using set builder notation. In reality, in real math, when you see real math going on. So here's some examples. Um, here I have a set, and here I have an x, and we have that such that, and then x is greater than 0. This could be a pipe too. It could be like a little line, but it's read the set of all x such that x is greater than 0. And we can look at this one. We can see the set of all x such that x is not equal to 11. That's how we read that. And the set of all x such that x is less than 5. So those are some examples of how we do it. And in a lot of cases, we'll have some sets that we refer to in there. So we may say that x is an element of something, one of these sets. And these are really common. We've studied them before, back when you were in M2 and again in M3. So N is the natural numbers, and Z is the integers, and Q is rational numbers, and R is real numbers. We haven't really gotten to imaginary numbers or complex numbers yet. But and when I'm typing these out, a lot of times I don't use the actual this font style on these, so we may just use a capital N and a capital Z and a capital Q and a capital R, and pretend. So so you'll see those, but you'll need to remember what those mean. Let's practice writing something in set builder notation. This is going to be a freebie. You've got three practices, and just write a note and then check yourself. And then there's one question at the end, just like I've been doing before, which counts for points. So the set of all q in Z. So q is an integer, and we're going to need to use that element symbol right there, such that q is any number between 2 and 6. So we're going to need some greater than or less than or greater than or equal to, etc. Symbols here. And it's between 2 and 6, so it doesn't include 2 and 6. So go ahead and try and write that out. Do your best. Okay, let's check. Did you get that? Let's see. So this is the set of all q in Z, so it's an element of Z, it's an integer, such that, and here I'm using that bar, but you could use a colon. 2 is less than q is less than 6, and this is read as q is between 2 and 6. All right, we've got two more practices to do. The set of all p in Z, so this is p is an integer, and you'll need to use that same notation, such that p is any number between 2 and 6 inclusive. So inclusive means it includes 2 and 6. So p can be 2 and p can be 6, and the last one, p couldn't be 2 and p couldn't be 6. So I'm going to give you a couple of minutes. Take your time, write the note, and then come back. Okay, let's check. This is an answer, and yours should look approximately like this. This is the set of all p in Z, so p is an integer, such that p is greater than or equal to 2 and less than or equal to 6. So it's between 2 and 6, and it includes 2 or 6. All right, last practice here on set builder notation, and then we'll have a real question. This is the set of all n such that n is any number greater than or equal to 2 and less than 6. So over here, it can be 2, but it can't be 6. And this is n, and we don't say what n is, so it's we don't know if it's an integer or whatever. If we don't say it, then generally you have to assume that it's a real number. So go ahead and write that note quickly. Okay, so here's the answer. The set of all n such that n is greater than or equal to 2, 2 is less than or equal to n is less than 6. So that number is greater than or equal to 2 and less than 6. All right, so here's your real one. The set of all x such that x is greater than 0. So go ahead and write that answer for me. This one counts. Be careful. Okay, so here's what you should have had, and we're going to go ahead and move on to talk about Python. This is difficult because most of the time we're using set builder notation. We're not using finite sets, we're using infinite sets, so there's not really a good use for that in computers. Computers don't deal with infinite sets well. They don't deal with irrational numbers well. There's a lot of rational numbers that they don't deal with well. But there is a library in Python called the Set Comprehension Library, which tries to help you use something similar to Set Builder. And if you want to investigate that, you can. But we're not going to do it today. It's way beyond what we're going to do in this 2-day camp here. Our next topic is a complement. What is a complement? And so we learned about the universal set last time, and we learned about sets within the universal set. But what if we want to talk about a situation like this, where we really want to know about the yellow? We don't know what we're going to do with that. We can't say it's the universal set because we don't want the set A, and we can't say it's set A because it's not none of set A is in there. So what do? We have a special notation that we use, and we call it the complement. So that means this is A, and everything that is not in A, but in the universe, of course, is the complement, or sometimes it's called not A or A not. And this little, it's not exactly an apostrophe over here, but this little dot over here, this little mark over here, is read not. And when we get into second quarter after midterms, you'll see that when we're doing logic, we use the same thing, and it means not there too. So it's read not a lot of times. It's either not A or A not, or the complement of A. So those are all okay, but because logic calls it not, then we refer to it as not, and that makes sense because it's not A. It's not A. It's everything that is not A. So it's okay to read that, and then some people read it A not because it's in that order, A not. So some people get lazy. So here's our first practice to finding the complement. Given U is equal to single digits, so single digits will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And the set B is equal to 0, 1, 4, 5, 6, 7, 8. Find the complement of B. So the first thing we want to do is we want to write out basically a Venn diagram for this, and here it is. So we put all of the digits on, and some of them are inside B, and some of them are outside B. So I want you to go ahead and tell me what the complement of B is, and remember that that the complement of B, we write it like this, not B or B not. Okay, so go ahead and try that in the notes. Okay, is that what you got? Now this apostrophe doesn't look exactly right, but I don't have anything on my keyboard in this font that looks good, so that's what I went with. So I wish we had LaTeX. So B not, not B, the complement of B is equal to the set of 2, 3, and 9, because B is the universe is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and B is 0, 1, 4, 5, 6, 7, 8. So these are the numbers that are left. Let's practice finding the complement again. Given that the universe is the letters in the alphabet, and you'll hear I see I used an ellipsis, and the set X is A, B, C, D, E. Find the complement of X. So think about what Venn diagram you would draw here. There we go. That's what it would look like. And so this is X, A, B, C, D, E, A, B, C, D, E, and then this out here is not X. It's not X. It's the complement to X. So I want you to go ahead and try to write that down. And remember, you can use ellipses. Okay, so this is what we got. You do not have to have exactly this, so you don't have to stop exactly at H, and you don't have to start exactly at X. But most of the times when we use an ellipsis, we try to have 3 things so that the pattern is obvious, because it is really what we're saying is follow this pattern. So we're following this pattern and keep going. So yours should look something like this. All right, so now it's time to do a check. Find the complement. U, again, is the letters of the English letters, the letters of the English alphabet, and X is A, B, C, D, E, and Y is E, F, G, and we want to find the complement of Y. So go ahead and do that now. Write down the complement of Y. Okay, let's check really fast. All right, so this is what our Venn diagram looks like for that. So here's EFG, and your answer may have looked something like this. Okay, so what about Python? Well, let me switch over to my coding environment here. I know it takes me a second every time, and I apologize for that. So Python doesn't really have anything called a complement, but and there's no universal set. There's no universe set. So what with which we talked about before when we were doing the universe, right? But we can define the universal set. So if we define the universal set as again, we'll just do that kind of example that we had previously. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If we get the single digits, okay, then we can use what's called the difference. So we can kind of find the difference between the set U and another set. So if we have set A is equal to say 1, 1, and 2. I thought I forgot my braces there. Then we can find the difference, and how we do that is we do it the same way we did before. There's an attribute, so we'll take set A difference and set U. Okay, so there's no difference there because the set A is smaller. But if we do it the other direction, which is we find the difference between set U and set A, then we'll get everything that's missing, missing from set A that is in set U. And there it is. And so if we define set B as 0 and 5 and 6, I told you I'm not that great of a programmer. And we can find the difference between set U, which is our universal set, and set B. So there, that is our complement. That is our complement to set B. And we could actually define a method by saying you could actually just say that the complement means set U difference, and then we can ask for the complement of set A, and well, there we go. Okay, spelling is good. Okay, so we can define complement as the difference of the universe. But remember, we'll have to define the universe set if we want to do that. So there is a way to do it. Our last thing today, we're going to talk about intersection. And I think this is going to be pretty easy for you because you've done Venn diagrams, and we've talked about Venn diagrams, and we've talked about the intersection of Venn diagrams, but we haven't actually used the notation for it. So you're just going to have to learn to use the notation for it. So over here, I've got let x be 1, 2, and 3, and y is 3, 4, and 5. So the question is, what elements do x and y have in common? And that's a really common question in real life. We've got two sets of things, and which ones are the same, which ones are in both. That's a really common question. So how we define that is by using this notation up here, which looks like an upside down U, and it's an intersection. Okay, so it's the intersection. So it is in both x and y, and that's going to be important. Remember that it's in both x and y, because later we're going to have another symbol when we do logic that looks very similar to that. That means and. So and there's a reason that they're the same, because it's in x and y, and the answer is 3. So this little upside down U. So we got a couple of practices here. So let's practice finding the intersection. So my universe is the counting numbers, and P is multiples of 3 less than 20, and so that's 3, 6, 9, etc. less than 20. and Q is the even numbers less than 20. So 2, 4, 6, 8, all the way to 20, and we want to know what the intersection of that is. So of course we're going to draw a Venn diagram to do this. So we've got our multiples of 3. 3, 6, 9, 12, 15, and 18, and we stop at 20. And for Q, we've got our even numbers, 2, 4, 6, 8, 10, 12, 14, 16, and 18. We want to find the intersection. We want to find the ones that are in the same in both. So I want you to go ahead and write that out. And you can type it out. Type the word intersection out if you want. If you know how to do this symbol, you can copy and paste it from my question, or you can do you can find it using Unicode. Okay, so your answer should look like this. That's fairly straightforward. 6, 12, and 18 are in both. So the intersection of P and Q is the set 6, 12, 18, and P and Q. Okay, so we're going to let C be these 3 letters here, and we're going to let D be these 7 letters here, and we want to find out which letters are the same in both sets. And so that's the intersection. What letters are in this word that are also in this word? And so we're going to find the intersection of C and D. So I want you to think about how you would draw the Venn diagram for this for a second. Okay, and here it is. So we can say that C is a subset of D, right? You can say C is a subset of D because C is completely contained within D. Everything that is in C is also in D. And here we want to write out the intersection. So you can either copy and paste from my question, or you can or you can use the word intersection if you can't figure out how to do that. Okay, so here's our answers. The intersection of C and D is A, R, and E, and A, R, and E is the same as C. And why is that? Because C is a subset, so there's nothing outside to cut off from C. So when we have a subset, this is actually actually something fairly useful in mathematics. When something is a subset, and you take the intersection, you just end up with the subset instead of the superset, the larger set. Okay, so here's our check. This is our last thing to do on the presentation here. So let B be the set of band members. So B had the band members. There are Sam, Lori, Rowie, and Derek. Let C be the set of chorus members. So the set C is Derek, Keisha, and Robin. So we want to find out who is in both band and chorus. And so we need to find out where the intersection is. So we're going to find the intersection of B and C. What kind of Venn diagram would you draw? Does it look something like this? Okay, so go ahead and tell me what the intersection of B and C is. And this one counts. Okay, so what about Python? I'm going to switch over to my coding environment here. And I think I'm going to exit out and clear here to make it nicer. Okay, so I'm going to define a couple of sets. I'm going to define my set A as, you don't have to use set A and set B like I always do. You can use whatever definitions you want. 1, 2, 3, 4, 5. And I'm going to define set B as 3, 4, 5, 6, 7. So if I want to find the intersection, then again I'm going to use an attribute. So it's an intersection with set B, and there I can find the ones that are the same. And it doesn't matter if that's not what I want. It doesn't matter if I put set B first or set A first, because the intersection for them just doesn't matter which order it is. You'll get the same answer either way. It's different than when we were doing the complement, right? So we wanted to use a difference, and difference there mattered, but intersection here doesn't matter. The same results either way. And if I define set C equal to 5, 6, 7. I'll tell you what, let me do one. Okay, set C is 5, 6, 7, and I want to know the intersection with set C and set B. So here we've got 6, 7, 8, and here we've got 3, 4, 5, 6, 7. So the intersection, the ones that are the same on both 6 and 7, and if I wanted to find the intersection of set C with set A, I get the empty set, because set A is 1, 2, 3, 4, 5, and set C is 6, 7, 8, so they're not touching each other. Well, that's our presentation on intersections and complements and set builder notation. So go ahead and meet me back in Discord, and we'll go through your coding assignment. See you in a minute.